we are ready to progress. And the next speaker is Dr. Lluis Corominas. He holds a PhD in environmental sciences and a master in environmental engineering and postdoctoral experience in Canada, working with Professor Peter Vanrolleghem. He's now a junior researcher at IES and focuses his research on the development of tools and methods to improve the management of urban wastewater systems. So we stay in the same, let's say, application field. His expertise is on modeling, control, and life cycle assessment. He has been involved in national and international projects, among which some projects funded by the European Union, like probably, I don't know if you will talk about new sustainable concepts and processes for optimization and upgrading municipal wastewater and sludge treatment. The acronym is much shorter, NEPTUNE. He is now principal investigator in Marie-Curie Action, Ecosystem-Based Management Strategies of Urban Wastewater Systems, EcoMaWat. So I lend the mic to Lluis.
Thank you for the long introduction. I'm going to talk about combined sewer overflow. So we go to the sewer system now, and the presentation is about monitoring and understanding how the system behaves. This project is collaboration between ICRA, the Catalan Institute for Water Research, and UPC, which is University in Barcelona. And UPC is expert on that, are the experts on data mining, and we are the experts on monitoring, getting data, and processing the data. So the presentation. Okay, here. The presentation is divided into these sections. So first the problem statement, then I will introduce the case study. I will talk about the data management system that we have developed to collect the data, organize the data, and then to pre-proceed the data. The data interpretation, so here having the data mining techniques, and finally the results and the conclusions. Looks like. So going to the problem statement, we go to the combined sewer systems. Under dry weather conditions, normally the sewer systems collect the wastewater from the houses and transport that wastewater to the wastewater treatment plants. So this is the left situation that you have in there. However, sorry. Yeah. However, under wet weather conditions, the runoff water ends up also, you see here, ends also into the sewer system, and then the maximum capacity is exceeded. And when this happens, this mixture of rainwater and sewer and domestic wastewater goes to the receiving water bodies. This is especially tricky in the Mediterranean catchments when we have very low flow rivers, very small rivers, and there is no dilution capacity. So this problematic situation is exacerbated in these Mediterranean countries. So, really? So, also from the problem statement, if we want to monitor this, if you want to see how this behaves, we have to install sensors, we have to get data, and normally it's not that easy because you don't have, it's a severe environment, so it's a very complicated situation that you have in the harsh conditions, have severe conditions. You have to monitor multiple CSO structures. It's not about just getting it at the wastewater treatment plant, measuring at the influent or at the effluent. You have many places where you have to monitor at the same time, and this is limiting as well the budget. The devices, if you want to measure flow, the devices that measure flow are very expensive, and if you multiply by 13 places that you might have in 7 kilometers, this might be extremely expensive. So, and also when you have this amount of sensors, amount of data, then you need to interpret. So each structure will behave differently or similarly, but we need to interpret that as a single data set, let's say. So two things are important: to develop low-cost monitoring devices. This is important, and here I want to stress the paper of Gustav Olsson 2012 about monitoring and control of wastewater treatment plants and water systems, where there is a need for low-cost monitoring to get to collect data, even if it's not the perfect data that you would like to have to properly manage the system. And the other thing is that we need this data mining to interpret the outcomes from these devices. In the case study, we're located northeast of Spain, and so we are located northeast of Spain, and just north of Barcelona we have this catchment, and the catchment overall discharges just north of Barcelona, and we just focus on a very small place there. It's not. In a small subcatchment there. The characteristics of that small subcatchment are presented in this more detailed scheme here. So we have a drainage area of 370 hectares, 15,200 inhabitants, 7.3 kilometers of combined sewer system, and we have 13 CSO structures to monitor. It's a relatively a small system. We wanted to start with a small system to perform this validation. So you see here the system, and the wastewater treatment plant is located at the very end, so the water flows in this direction. Okay, the measuring campaign that we perform is almost 1 year of getting data from the sensors, and we could get 53 rain events and analyze. So for the data management, we develop a new approach, which is going to be patented and is going to be submitted to a journal very soon, where we determine the duration and frequency. We are not able to determine the flow that we have in each CSO structure, just duration and frequency. So then we relate each rain event. We have information from the rain gauges to the CSO events in each structure. And finally, we structure everything in 2 tables. We have created 2 data sets, one focused on the CSO structures, so on the 13 CSO structures, and another one that is mainly driven by the rain events, so having all the 53 rain events. So to better explain the the tables, the configuration. So for the first one, we have the CSO structures, the 13 CSO structures, and then we have some. It's not. I don't know where to point at. Really? Okay, everything appears. So there are some variables that are related to the physical characteristics of the system. Let's say the diameter, the distance to the wastewater treatment plant, or the type of structure, and then we want to link that or relate to the specific CSO behavior of that structure. So the overflow position, if it's the first structure to overflow or is the last one, the time overflowing and the number of overflows that it presented. In a second table, what we do have is the rain events, the 53 rain events, one next to another one, and we have several fields there. We have the rainfall characteristics, the intensity, and the duration, and then we have CSO global behavior. So on average, for that rain event, it was that time overflow and that number of overflows, and we have a specific behavior as well. So we also have fields for each CSO structure there, showing the overflow position and these characteristics. So the architecture of the software that we develop is that we have the sensors, we have the data that we want to collect from the CSOs and from the rain gauges, and we get this into our databases. So we have a data acquisition module. We have a GIS interface where we locate our CSO structures, and it can also be used to get the last. So this is giving you the last values, and also it can create some alarms. You get a green if everything goes fine, or red if something goes wrong. So, but very simple stuff. And then from the rain gauges, some are giving values automatically, but you always find people that have rain gauges. They have some devices at home or at the institution, so you go there, you get the data, so you can also import that data, so you have double verification. So we have created a tool to import that data. And then we have a visualization module, so we can create graphs and see what's coming out of the system. This is very flexible. You can add any variable that you want. You can also detect outliers if you have some outliers in there, and you can easily see what happened in the system. We also have alarms. If the device is not working properly, you get an alarm. Says, okay, you have to replace it. You have to make some modifications. So you also get alarms from the system. And finally, for the data analysis module, what we decided to do is to connect to R. R is a free available software. I have to say that everything we use is available for free. So we interact with R, and any algorithm control chart that we want to develop, we will do it on R. So we send the data to R, the analysis is conducted there, and we get the values back. For this study, however, we used JSCOND and Weka. These are two software platforms that allow to implement these data mining techniques that we have used. So, but the future is to implement these data mining techniques in R. An example of what's happening and how we present this, so what we have here is that there's no overflow here, and then we have all the overflow structures in that axis. So for one episode, this is a one rain episode. As the time goes on, if we go up in one of the sensors, we see that this is overflowing, and then it goes down, but then it starts the next one. This is overflowing, goes down, and here with that representation you can see how the system is performing, but this is not enough to really characterize it. So another thing, this is what we did, is to automatically create these tables based on the data that you get. It means that you don't need to reorganize the data anytime you want to do the analysis. So it's automatically performed, and then you can do the analysis automatically. The data mining techniques that we use, very simple ones. So the data mining technique to cluster, do some clustering, and using mean distances, and normally what we came out with 3 groups of behavior of the system. We also created some association rules for extracting feature correlation rules from data. And we also created some decision trees to assess whether, to have some prediction capability to assess whether we have overflow or not according to several variables, if it's okay. So going to the results, the tool has several plots, so we can really see the total number of overflows of each structure. We can see that the most influencing structure, or the most potential dangerous structure, is the one nearby the wastewater treatment plant. So in terms of numbers of overflows, this is what we present here. Some structures almost don't overflow. And we can also present a kind of graph with colors indicating the more reddish, the earlier it starts overflowing for a given episode. So we again see that this overflow at the wastewater treatment plant is normally it normally starts overflowing earlier than others. And if we plot here the CSO structures, 12 CSO structures, then we have the number of overflows, and then the total time overflowing. We see that by far the structure 12 is the one having larger impact. This is an order of magnitude compared to the other structures. So by means of that technique, we identified this is the most weak point of the whole system. We have all 2 other structures that have a little bit of importance compared to the other ones, but this one had a huge impact. If we have a correlation there, we plotted the total rain volume and the total time overflowing, and they see that there is a positive correlation in there. And we also clustered that to see whether there were different behavior in different events. So we obtained short and weak events, short and intense events, and long and moderate events there. But we see as well that the system is really reaching maximum capacity. Even with low rain events, it is overflowing. So it's quite kind of complicated. The need for an upgrade. This is really necessary. we see that the long and moderate were during autumn and spring as well. We identified that. Regarding the patterns of CSO behavior, we see that normally the overflowing situation starts over there and propagates backwards. So this is something we extracted from the data as well. And as a first attempt conclusion, if we want to install stormwater tanks, we should do it before the CSO structure 12 in the wastewater treatment plant, or this CSO structure 3, still to verify it with managers. Then we use this associative analysis to check whether there were correlations, and we saw that that CSO, which is the most important, is highly correlated to the other structures, what means that for us doing intensive monitoring of this structure would be very important, and we can extrapolate, or we could have an indication on what's happening within the other structures, facilitating maintaining tasks afterwards. We also saw other types of correlation indicating that if there's no CSO in all these structures, it was just for weak rains, and then we also saw that if it's overflowing everywhere, it is for really strong events, but this is really redundant, I would say. This is this is what we propose, to have intensive monitoring. In that one we get a lot of information in the whole system. Finally, in the last part of the results, we performed discriminant analysis to have a little bit of prediction capacity, to have a decision tree for each structure. Problem is that we got a few very simple trees, but then we got some complex trees, and then you need some pruning techniques to increase to reduce the dimension of that tree, the complexity of that tree. But at least we have some prediction capability there. This is an example of one of the decision trees. Yeah, where you
get some questions.
Yeah, this is the last slide. So you have one example of the decision trees where you get no overflow, yes overflow, depending on several variables that we have considered in the analysis. And just the conclusions that, well, the data mining techniques were useful to interpret and to characterize the system. That's all.
Questions?
Stefan Meijers, the Netherlands. Thank you, Lluis, for the nice presentation. It was clear. In this case, you relied completely on monitoring to understand the working of the system. Have you also considered modeling the network and from that on trying to see if you see the same behavior?
Yeah, this is the natural continuation on that. So we have been doing also modeling using SWIM, and we are going to calibrate the model using this valuable information. Normally these models are calibrated using flow sensors in the sewer system, but they are not really considering what's happening in the overflows, unless the next presentation is doing that. Could be. So I think this is valuable information. As I told you, it's not, you don't have the flow at each structure, but at least you have information on what's happening, if it's overflowing or not, and this can increase the accuracy of the models that you have.
There's a question there.
Hello, Annelies Aert from Technical University of Delft. I had a question, especially with these overflows. There is a lot of uncertainty on the data, and I think also on modeling results. Do you think that in this case, actually, the human sensors are a good option?
Sorry, the human?
The human sensors means that actually you use the complaints and the information from overflows given by
I think the best information you get is from the operators. It's amazing how they know the system. You go there, you ask, and they, well, do you know which? They already. I think that they already know which is the most dangerous system or the most impact system, and they always found explanations on our sensors. Oh, this is not working because you have this problem. This is working great.
The question is more about
social
sensors with people. Sometimes you can really check out the overflow or smell it sometimes.
Well,
yes,
yeah. But
wouldn't you consider the usage? Because I think it's very costly to instrument the network with the sensor that you have deployed. would not be sustainable at a larger scale. So do you think that social information, people tweeting about what they
this is what, maybe
it would be a complement?
Maybe it would work. Is this similar to the presentation that you showed before? Could be something that we could, that's true. That's true.
Thank you.
Any other question? I have one, that is a little bit of a provocation. You said that you were using WCAS or the public domain software, right? But also you mentioned the patent. How are you keeping together these two things?
Well,
using public software but patenting the algorithms.
Well, we're not going to patent the algorithms. We want to just patent the technology, low-cost technology. That's why I presented that. Otherwise, I would not have presented that at the conference. But
in the sensor?
The sensor, the type of sensors. But regarding the data management system, everything is available. I mean, this clustering or data mining techniques, you have many softwares that do that, so we do not aim to patent anything related to that.
Thank you.
Thank you.
So last but
not least,